My name is Juanjuan. At this work, replicated additive secure sharing with optimized number of shares is accomplished with my other collaborators at Chinese Academy of Sciences. My presentation includes the following parts: introduction, 2LN replicated secret sharing, TLN replicated secret sharing, and evaluation. For this part, I will first introduce the concept of additive secret sharing. Additive secret sharing splits the secret value with the number of shares, whose sum is equal to the secret value. We denote the secret value as S, and the shares as S1, S2, etc. Replicated additive secret sharing, referred to as RSS, is proposed to achieve threshold feature. Each party holds more than one share and chooses some correct shares when collaborating with different parties during secret reconstruction. Additive secret sharing is more popular than Shamir secret sharing in secure multi-party computation because of its efficient computation, while the storage overhead is not as good. Additive secret sharing is widely adopted in privacy-preserving machine learning at threshold signature to protect user information at signing key from leakage. Existing schemes have inherent shortcomings. Some have efficient storage. Each party holds combination N-1, T-1 shares in TLN RSS scheme, ISN. Some have inefficient computation. CGI and KCI achieve threshold by converting Shamir share into additive share, which brings huge computational overhead. Some apply to fixed threshold, like 203 or 204 ISS realized by AFL+, ABY3, pre-PY, etc. Our scheme overcomes above problems, and the computations are summarized in three aspects. Firstly, we design a new 2LN RSS scheme and prove the optimal storage overhead theoretically. Secondly, we extend the optimal 2LN RSS to a general TLN RSS with an arbitrary threshold. And the analysis demonstrates that it needs much less storage compared to prior works. Thirdly, our scheme supports the dynamic joining in of a new server, which generates a new share while the existing shares remain unchanged. Our scheme consists of a dealer and multiple parties. In TLN RSS, dealer accomplishes threshold by giving each party multiple shares that any group of T or more parties can together reconstruct the secret, but no group of fewer than T parties can. We assume that an adversary in our scheme can be divided into two kinds. An eavesdropping adversary learns all the information stored at the corrupted parties. A hunting adversary may also disturb corrupted parties to stop sending messages. Our scheme can tolerate up to T-1 eavesdropping parties and up to N-T hunting parties. Besides, we assume that the dealer is a trusted party. Our 2LN RSS generates shares incrementally by adding parties one by one in turn. Multiple share sets will be generated, and each share set contains two shares, whose sum is secret S. We denote a secret share as S sub A super B. Subscript A indicates the order of share set that share belongs to, which is related to the number of parties. Superscript B indicates the order of a share in its share set, which is 1 or 2. Specifically, in 2LN replicated share generation, dealer generates round-up log to n sets of shares, allocates one share in first share set to P1 and the other share to P2. Then, considering a new arriving party Pi, I within range 3 to n, dealer operates as follows. Step 1. Copy shares. Dealer copies shares of one existing party to Pi. This existing party is denoted as P conflict, and ID conflict equals to I minus 2 power of round up log 2I minus 1. Since our goal is to make parties possess a minimum number of shares, we choose one of the parties holding the minimum number of shares at present as p-conflict. Step 2. Allocate new shares to two conflict parties. Since pi and p-conflict hold the same shares, they cannot reconstruct the secret. In order to solve this, dealer allocates one share in log 2i's share set to p-conflict and the other share to pi. Take 204 RSS share generation as an example. In 202 RSS, dealer samples two additive shares S11, S12, and sends to P1 and P2 respectively. 203 replicated share generation is based on 202. Dealer copies P1's share S11 to P3, then generates a new set of shares S21, S22, and distributes to P1 and P3 respectively. 204 replicated share generation is based on 203. Dealer copies P2's share S12 to P4 and distributes new shares S21, S22 to P2, P4 respectively. So far, choosing any two parties from our 4 can reconstruct secret S. In 201 unreplicated secret reconstruction, to reconstruct parties are PID1, PID2, where ID1 less than ID2. In step 1, dealer computes conflict ID of larger party PID2, which is ID2 minus 2 power of round up log 2 ID2 minus 1. In step 2, dealer compares conflict with ID1. If conflict equals to ID1, which means shares of PID1 were copied to PID2 during share generation, so PID1 and PID2 can reconstruct the secret using their first different share, which is round up log 2 ID2's share they hold. If conflict not equals to ID1, since shares of p-conflict are copied to PID2 during share generation, PID2 can use these copied shares to reconstruct secret with any party whose ID less than ID2 and not equals to conflict. Obviously, ID1 satisfies this case, so PID2 routes its ID back to conflict. Next, rearrange to reconstruct IDs. Set larger ID as ID2 and smaller ID as ID1. Then execute step 1, step 2 in loop until conflict equals to ID1 holds. Take 204 replicated secret reconstruction as an example. Assume reconstruct parties are P1 and P4. The conflict ID of P4 can be computed as 2. P1's ID is not equals to 8, so P4 routes its ID back to 2. Next, computing conflict ID of P2, which is 1, so P1 and P2 choose the round up log 2's share to reconstruct secret, which is computing conflict ID of P2, which is 1, so P1 and P2 choose the round up log 2's share to reconstruct secret, which is S11 and S12. There are also some scenarios that requires larger threshold, and we extend threshold to an arbitrary number to achieve TL1 RSS. Dealer generates shares in an incremental way like TL1 RSS. It starts from T of T RSS, then to T of T plus 1 RSS, so on, and finally T of 1 RSS. In T of T RSS, dealer samples T random numbers as shares S11, S12, so on as 1T, whose sum is secret S, and distributes one of them to P1, P2, PT respectively. Then T of T plus 1 RSS is generated based on T of T RSS. Dealer allocates P1's share S11 to PT plus 1. Non-secret can be recovered by first T parties or the last T parties, while any T parties including both P1 and PT plus 1 cannot. In order to solve this, dealer samples new share S21, S22 to P1, PT plus 1 respectively, then computes delta 1 equals to S minus S11 minus S21, and generates T minus 2 of T minus 1 RSS of delta 1. among rest t-1 parties. In this process, recursive algorithm is required. When achieving T of T plus RSS of S, subproblem T-2 of T-1 RSS of delta 1 will be called, in which subproblem T-4 of T-3 RSS will be called, until the recurrent reaches its bound 2 of 3 or 3 of 4 determined by whether T is even or odd, respectively, since T reduces by 2 in each recurrent. Similar to T of T plus 1 shared generation described above, then add P, T plus 2, so on, Pn in order. When Pi is added, dealer executes as below. Copy Pi minus T shares to Pi. Sample new shares S*1, S*2 to Pi minus T, Pi respectively. Compute subsecret delta equals to S minus S*1 minus S*2, then generate T-2 of I-2 RSS of delta among existing parties except P, I-T, and Pi. In this process, recurrent will be called until reaching its bound that threshold is 2 or 3. 3 of n RSS is designed similar to 2 of n RSS. Thus, it will not be described in detail here. In T of n RSS, the maximum number of shares held by each party is denoted as f max level Tn, which is a recursive function related to T and n. F max level is round up log to n if T is 2, n minus 2 if T equals 3, add f max level T n minus 1 plus f max level T minus 2 n minus 2 if T is greater than 3. Let's take 406 share generation as example. In 404 RSS, dealer generates 4 shares S11, S12, S13, S14, and distributes them to P1, P2, P3, P4 respectively. Next, 405 RSS is generated based on 404. Dealer copies P1's share S11 to P5, generates new shares P21, P22, and distributes to P1, P5 respectively. Then dealer computes subsecret S minus S21 minus S22 and generates 2 or 3 RSS of it among P2, P3, and P4. 406 RSS is generated similarly based on 405 RSS. In T of n replicated secret reconstruction, firstly, T reconstruct parties exchange IDs and then obtain reconstruct ID list, ID1, ID2, so on, IDT, where IDs are sorted in ascending order. Then each party should select a correct share from its multiple shares. Finally, ending all shares selected by T parties will reconstruct secret. The selection starts from maximum ID IDT. Computes conflict ID of IDT is IDT minus T. If P conflict is a reconstruct party, which means that dealer copied shares from P conflict to PIDT during share generation. Therefore, P conflict and PIDT shall choose the first different share which is generated after T of IDT minus 1 RSS. The rest parties execute the secret reconstruction algorithm in a recurrent, and with the threshold T minus 2 after 2 complete parties are removed. If P conflict is not a reconstruct party, which means shares of PIDT that are generated after the conflict will not be used. Instead, PIDT will choose one from shares copied from P conflict. Thus, PIDT rolls its ID back to conflict. Then reconstruct parties sort IDs or refresh reconstruct parties in ascending order, and execute step 1, step 2 in a loop. If no parties are in conflict, each reconstruct party chooses the first share in the present recurrent to reconstruct the secret. We evaluate the storage and computation overhead, set up shown in PPT. Existing schemes realize 203, 204 access by having each party held 2 shares. Our 2N RSS or 3N RSS replicate share generation extends the number of parties to an arbitrary n by having each party hold round up log 2n shares or n-2 shares, which obtains the same storage cost as existing schemes when n is 3 or 4. We compare our scheme with ISN in the case that T is 4 and n ranges from 10 to 50. The experimental result shows our storage efficiency is up to 2 orders of magnitude faster than ISN. Runtime of replicated share generation is shown in the first table. Only millisecond generation time is required when T is 2 or 3, while runtime explodes when both T and N are large. For example, runtime of 10 of 60 share generation is 10 minutes. Runtime of distinct reconstruct subsets are different, so we test a large number of distinct subsets and finally take the average. It only takes 1 or 2 microseconds for each party to select the correct share when T is 2 or 3, and only 400 millisecond selection time is required in 10 of 60 secret reconstruction. Do you have questions?
Hello everyone, my name is Hanyu. The title of our paper is Generic Two-Party PFE with consistent runs and linear additive security and efficient instantiation. First, I will introduce SFE and PFE. They are two cases of MPC protocols, security function evaluation and private function evaluation. Depending on whether the function is public or private. In SFE, the function is not private knowledge of any participant, but an open function that all the parties agree to compute. Suppose there are parties Alice and Bob. Alice has private data X. Bob has private data Y. At the end of SFE, Bob are given fxy. Alice can also get fxy, but any party's private data is not disclosed to any other parties. In PFE, the function is private knowledge of Alice, who collaborates with data owners Bob to generally compute fxy. Alice also can also have no private data X. The final result is fx. At the end of PFE, the final result would be obtained while the private knowledge of each party is not disclosed. In this paper, we have designed a two-party PFE protocol. MPC security is generally divided into a semi-host adversary and the malicious adversary model. In semi-host adversary model, each corrupt party follows the pre-GSI protocol steps, except that he is curious but tries to inform as much as possible other parties' private data from the transcript. In malicious adversary model, corrupt parties can divide from the protocol arbitrarily. Besides the ability in the semi-host adversary model, these corrupt parties can also take any action during the protocol execution. In this paper, we focus on the malicious adversary model. We have divided the roles to release PFE into three. The overhead of UC-based SecureComm is this. The best asymptotic set of valence UC is this by Liu et al. And seems to reach a theoretical optimum. Beyond the UC-based has the following technologies. We designed generic PFE, but don't design two-party PFE with constant rows and linear active circuit. We found that Beecher et al. And Liu et al. Designed a reusable two-party PFE and semi-host adversary model and malicious adversary model, respectively, based on DDH. And these are constant rows and linear overhead. This is here to only one concrete design of actively secure two-party PFE with constant rows and linear complex, particular suitable for scenarios where factions can be reused. Our goal is to generate two-party PFE with constant rows and linear active circuit for non-reusable private faction whose instantiation made achieving less computation and communication consumption. Our protocol is based on gable circuit. We start by analyzing the gable circuit. At the heart of gable circuit is create gable truth tables. The gable randomly choose where case to create gable truth tables. We take the circuit case as an example to briefly describe how the gable truth tables is generated and described. This denotes symmetric description of the plain text M with symmetric K. This indicate that the input where A is a 0-bit and 1-bit random where case respectively. Similar for this and similar for B and C. The gable creates the gable truth table. First create the truth table with random where case, then encrypt the truth tables. At the end, gable the encrypt truth tables. The gable sends the gable tables to evaluator. The evaluator can only get one of the pair for where case to describe the row in the gable truth table. The security of the gable circuit is that the evaluator can only get one of a pair for where case and can't distinguish whether the where case the where case is using 0-bit or 1-bit. The pair of where case is sufficient as long as it satisfies randomness. We then introduce the instant combination EP hereafter. Figure A shows a simple circuit with 5 input wires, 4 gates, and 2 output wires. Each of these gates is 2 fan-in and any fan-out. We define the following. Output gates in figure A are G3 and G4. Non-output gates in figure A are G1 and G2. The incoming wires of circuit gates are abbreviated as IW. The outgoing wires of circuit gates and the input wires of circuit abbreviated as OW. The output wires of circuit in figure A are Y1 and Y2. Figure B shows the EP relationship between OW and IW. We represent the EP relationship with by pi f. The ZKEP is a generic zonology protocol to prove that EP is correctly executed. ZKEP consists of three feathers: dummy placement feathers, representation feathers, permutation feathers. Each feather has a zoology protocol. If all feathers are proven, the EP is concrete. The ZKDS measures the ZK EP protocol and consists of two succeeding components. Both components use the ZK shuffle protocol to prove the concreteness of affiliation. If both components are proven, the EP is concrete. We can see that the ZKDS is better than the ZKEP. We found that constructing an active circuit PFE can be divided into two parts. One is to build a passive circuit PFE, and the other is to build a valued primitive to prove to the data owner that the function owner performs the EP optimization correctly. We perceive that the ZEP can be directly plugged into passive SecureComm to produce actively Secure two-party PFE. This will not work for ZK due to its particular structure. We designed a generic two-party PFE with constant runs in linear active circuit security by ZKDS. This is our protocol. Alice translate here private F into a circuit CF, which has U input wires G and S and O output wires. Alice sent U, G, O, and C to Bob. C is this. C randomly choose two sets of random numbers and encrypt them and PK. Bob holds the private data X. He generate this and send PK to Alice. Here, Bob only generating n reduce O of random wire case, and this represents base zone. He encrypt first k wire case with PK and sends this the subtext to Alice. Alice applies pi1 and randomization to this subtext to obtain n reduce O new subtext. Their plain text can represent the where case of OW. Alice copy this subtext to 2G subtext according to C. we denote this set as this. She applies pi2 and randomization to this subtext to obtain to GNU subtext. Their plaintext can represent the where case of IW. Alice sends this subtext to Bob and applies ZKDS to prove the concordance of her execution. Bob described each this and recovers the new where case in preparation for constructing the GT. This represents the bit zoo of left incoming where case of GI. This represents the bit 1 of left incoming where k of GI. The right incoming where k and outgoing where k of GI is same. Now Bob can create gobble tables. He sends these gobble tables and where gobble tables and where case of replacing data X to Alice. Alice now knows the set and random numbers A and B, so she can describe the gobble tables to get the where case of replacing the result Y. She sends this where case to Bob. He can get the result Fx. The proposed two-party PFE protocol has active safety. We give the heuristic analysis in section 3.3. We demonstrate the protocol satisfies the active circuit using the real and ideal simulation paradigm in section 3.4. We recommend reading the paper to understand. We described the overhead of protocol in detail in our paper. We constant the total communication cost and hypothesis of protocol. In total, our protocol reduce approximately this communication cost and this computation cost compared to the first execution of LWY22. Our protocol even outperforms the original KM11 and MS13 that are passively secure from the communication perspective. In conclusion, the proposed PFE and LWY22 thus make optimal solutions valuable for non-reusable and reusable private function respectively. We also raised two questions to think about. That's all. Thank you.